ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. So today we're going to be going over the second part of Chapter 4. We're looking at Chemistry, the 7th edition by Zumdahl. And just as a reminder, Chapter 4 is about types of chemical reactions and solution stoichiometry. So if you haven't seen that first part, it was getting a little long, so it's cut into two sections. So section 4.8 is about acid-base reactions. And so keep this in mind. The last couple of parts of Chapter 4 are a good introduction to a lot of things that you're going to be seeing later on, but there are two other chapters dedicated to acid-base reactions and equilibria. So just keep in mind, this is like the bare bones basic stuff you need to be able to know just for this part of Chapter 4. So the first part, what is an acid and what is a base? So there are a lot of definitions, and so the only definition that you really need to know in this chapter is the Bronsted-Lowry definition of acids and bases. So what is an acid? An acid is a proton donor. And think back to what we talked about when we were talking about protons. Remember, protons are positively charged, and so when we say proton donor, we're actually talking about a hydrogen ion. So we're talking about a positively charged hydrogen ion. If the substance we're looking at is donating that hydrogen ion, it's an acid. On the other hand, if it is taking that hydrogen ion, it is a base. So a good way of looking at Bronsted-Lowry acid-base reactions is kind of like this. You have two reactants, you have two products. So what we want to look at is we want to look at which one of the reactants is going to be the acid and which one is going to be the base. So in this situation, we can tell by looking at the products here that this hydrogen is going from this HCl to this H2O to make H3O+. And then what's left over is just the Cl-. That means that HCl in this situation would be our donor. So if we're looking at that in pictures, it looks like this. This H is going from here, and now it's sticking to the H2O to make H3O+. That means that HCl is my acid, and H2O in this situation would be my base. Another common example here, we have NH3 plus HF, and we're getting an NH4 plus F minus. So we have ammonia, we have hydrofluoric acid, and then we're making an ammonium ion and a fluoride ion. So again, think about which one of these hydrogens. Is a hydrogen being donated from here to here, or is a hydrogen being donated from here to here? So when we look at that pictographically here, you can kind of see that this H is going from the HF, the hydrofluoric acid, and now it's being attached to here, to NH3, to make this ammonium ion here. And so this would be my acid, so HF is my acid, because it is donating its hydrogen. NH3 is the base, and again, if you know the names of these, this is called hydrofluoric acid, so of course it's the acid. And most people recognize that ammonia is a base. And again, that's just how Bronsted-Lowry acid-base reactions work. You always have an acid, and then you have a base. One is going to be the donor, the other is going to be the acceptor. So what about strong acids and bases? So there are many strong acids, but this is the list that you need to be aware of. So we have perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and then we have nitric acid. The one that is suspiciously missing is hydrofluoric acid. So hydrofluoric acid is not, believe it or not, a strong acid. It's a weak acid. Okay, so if you're wondering, hey, why are these other halogens in the strong acid list, but hydrofluoric acid is not? Again, it's just because hydrofluoric acid is a weak acid. Strong bases, so we have our alkali hydroxides and our alkaline earth hydroxides. So we have lithium hydroxide, sodium hydroxide, and potassium hydroxide. Again, here for the alkaline earth hydroxides, we've got calcium, strontium, and barium hydroxide. Notice like beryllium hydroxide not on this list, so there are only really 6 strong acids and 6 strong bases that you need to be aware of. And keep in mind that whenever you react a strong acid and a strong base together, so you can pick any one of these acids and any one of these bases, you always end up with a net ionic equation that is H plus OH minus making H2O. You're always generating water in that situation. So in other words, the H from the acid here is always going to mix with the OH from the strong base in order to manufacture water. And then the leftovers are the spectators here. Like you're going to have, your in this case, like a ClO4 minus floating around, or you're going to have like, a Ca2 plus floating around or something like that. And so those are going to be your spectators. So there are different types of neutralizations that we can talk about then. One of which is one that we literally just talked about here, but strong acid by a strong base. So let's say we're doing a titration. Now, you don't exactly need to know what a titration is in detail yet, but I'm going to describe it to you. So a titration is a chemical technique where we have something that normally has an unknown concentration, and we put that in the bottom of an Erlenmeyer flask. You then have a burette, and you have something that is known. So in this case, it's going to be a strong base because we're neutralizing a strong acid by a strong base. So that means that if I were to label these, the strong acid would be here in the bottom, and I would know how much I have, but not its concentration. And then the strong base would be in the burette. And so the burette has these little divisions, and that means that you're going to be able to read and basically add a set quantity of this strong base into this strong acid. And what you're waiting for is you're waiting for pH changes, because the way that titrations work are that you normally get very, very small pH changes, and then at some point you get this drastic change in pH. And so again, you don't need to know the details of a titration yet, because again, there's a whole part of a unit that's going to be about titrations. But for now, keep in mind that this type of neutralization is when you have an unknown strong acid and you have a known strong base. And then by slowly adding your strong base to your strong acid and measuring the pH of your unknown strong acid here, you can make a graph that ends up looking something like this. And when you get your dramatic change in pH, that lets you know that, oh, great, I can figure out now using some quick little math what the concentration of this strong acid actually is. Okay, but keep in mind that for a strong acid and strong base titration like this, you're going to get your equivalence point happening at exactly a pH of 7. That's exactly when neutralization, go figure, occurs. And we call that the equivalence point. And again, that'll all be defined a little bit later on here. But keep in mind that this is the type of curve that you get. It's a kind of elongated S, and you always will start with some sort of pH that's low, because again, we have a strong acid here. And as you add little drops of even, or maybe even a milliliter at a time of this strong base here, what you're going to get is the pH is going to change and it's going to start to increase. And as it increases, eventually there's going to be like a point where you add just even one drop, and then you get this huge, gigantic change in pH. And so it goes from being acidic to being neutral and then basic very quickly. And when it does that, now you're adding extra base. And so now it's becoming even more basic. And so that's kind of how a titration is run. Okay. If you're wondering, how do I know when this point occurs? If you have a pH meter, it's really easy. Normally, we add indicator to the bottom of this. And so the indicator will change color, and it will change color pretty subtly as you get closer and closer to the equivalence point. And then eventually you'll have one too many drops and it will just shoot through the roof and you'll get a huge color change. But it's a pretty cool lab technique that we'll be doing later on. So keep that in mind. Now let's do the inverse. What about if we have the neutralization of a strong base by a strong acid? So instead, let's say we have a strong base in the bottom here and we have a known strong acid in the burette. So notice that it's the inverse. We now started with something that has a high pH, and as we add the strong acid, it's going to get neutralized, and so eventually we will reach a pH of 7 again, and that will be what we call again the equivalence point, and then it kind of drones off and we become more acidic. But again, notice that it is the exact inverse when you have the opposite, a strong base inside of your Erlenmeyer flask here, and you have your strong acid in your burette instead. Now you're probably thinking, okay, what are the other possibilities? So the other possibilities are going to be, what if you have weak ones? So anything that's not on that list. What if you have a weak base? So if you have a weak base, you get a lot more interesting stuff occurring. So the first thing that you should notice here is that first of all, we don't have the nice gigantic S curve. It's a little bit more subtle, right, than it was. And so what we sort of get here is we have, again, a high pH because we have a weak base here. And so you're going to get a lot more, let's say, a downward trend in the first part of your graph. Now, notice the equivalence point here is not happening at a pH of 7. It's going to be happening at some quantity that is below 7. And so when that equivalence point is hit, again, notice that we have like a process of it teetering off until we get to, a low pH again. But this is like your telltale weak base, strong acid titration, where again, we have kind of like this S curve, but it's a lot more subtle. And so what's going to happen is the equivalence point occurs lower than a pH of 7. Now think about the opposite, right? So what if we have a weak acid and a strong base? We have a weak acid in here, and we have a strong base in here. It's almost the exact same curve, but then notice that it's now going the opposite direction. So we have this slight increase as we're going up our titration curve, and then the equivalence point happens above 7. So notice the equivalence point is going to happen above 7 when we have a weak acid that we're going to be finding the concentration of here using a titration. And then again, it's going to teeter off, and you're going to get, again, a more basic as we get higher here, as we add more strong base, right? Again, those are just 4 things that you need to be able to identify. You don't need to be able to know really the whole mathematical process yet, because like I said, that's later on in another chapter. Now, how do you perform calculations for acid-base reactions? Again, the very simple ones are just strong acid, strong base, and that's pretty much all section 4.8 deals with. So the first thing you want to do is list all of the different chemical species that are present in the combined solution before any reaction occurs, and decide what type of reaction is going to actually be occurring. Go figure, it's an acid-base reaction because we're talking about acids and bases. Write the balanced equation for the reaction, calculate the moles of the reactants, determine the limiting reactant, which we did in chapter 3, if asked, if appropriate, and then calculate the moles of each of the required reactants or products as the question states. Convert from grams or volume of solution, if you have to, again, as required. So in reality, again, there's not going to be a whole lot of stuff, but here's some very brief definition things that you'll need to be able to be aware of as we go through this stuff. So what is a titration? Titration is, like I said, it's a lab technique, and specifically you're delivering a measured volume of solution. And what we call that the titrant. So that stuff that's in the burette is called the titrant. And you're adding it to a solution containing the substance that you were trying to analyze. And that's the stuff that was in the Erlenmeyer flask that we call the analyte. Now, the equivalence point is when you add enough titrant to exactly react with the analyte you have. And so that's, again, where you get that dramatic up or down kind of vertical part on your graph. Now, the end point, that's more like, let's say, visible. The equivalence point, you're not going to really be able to see that for the most part when we're doing acid-base titrations. It's just a clear liquid and a clear liquid. And when you're done, you're still left with a clear liquid. So we like to add, like I said, an indicator that changes color. And so the end point is going to be the point at which the indicator changes color, so you can tell that your equivalence point has been reached. But technically, the equivalence point and endpoint are not exactly the same thing. The endpoint is more of like, let's say, a range. Since everybody's eyesight's a little bit different, the equivalence point is a mathematically calculated part of your titration. So here we go. Let's do a titration here. We're going to mix some sulfuric acid, so again, strong acid, with sodium hydroxide, and that would be our strong base. How many moles of sodium hydroxide would be required to react with 1 liter of, again, a 0.500 molar solution of sulfuric acid in order to reach the end point of our reaction here? It should probably say equivalence point, but still, end point, again, they're not exactly the same thing, but we can calculate the equivalence point. End point, that's more visual, right? So let's write down our reaction here. So we have H2SO4, that's our sulfuric acid. We're mixing it together with sodium hydroxide. Remember, what did we say when you're mixing together a strong acid and a strong base? You're always going to be manufacturing water. So we have water being made, H2O, and then we have to think, okay, what exactly is left over here? So I have SO4 with a 2 minus, I have Na with a +1. Right? So that means that if I mix them together, I need to have Na2SO4, that's sodium sulfate. That would be made as my other product. So now looking at this, though, that really isn't balanced. So I would need to put a 2 in front of the NaOH, and I would need to put a 2 in front of the H2O in order to get that to be balanced. Now, let's actually deal with the numbers, right? We've got 0.5 molar sulfuric acid in 1 liter of it. So, using again all the stuff we just learned from chapter 4 here, I can find the number of moles. So, if I multiply zero point 0.5 times 1.00 liters, I get 0.500 moles of H2SO4. Now, notice I have my balanced equation. So, that means that I'm going to need double the amount of NaOH in order to balance and completely react with my H2SO4. So all I would need to do is take my 0.500 moles and multiply by 2. So I would need double, 1 mole of NaOH. And that technically answers the bolded slash blue part of this, where it says how many moles of sodium hydroxide would be required. Well, that answers that question there. Again, simple, easy. More on titrations later. This is not even really a titration question. So keep in mind, again, here's the thought process. Where are we going? We want to find this. How do we get there? I need to know what ions are being combined. I need to be able to balance that. I didn't even really need a net ionic equation because the net ionic equation would be kind of boring. It would just be H plus OH minus gives you H2O. And then I need to know, again, how many moles of H plus do I have? How much OH minus is going to be required in order to react with all of the H plus. And so again, that's just part of what we do when we're solving titration-based questions like that. All right, redox reactions. So this is the last part. Again, this is a good preview of chapters to come. Chapter 4 is weird in that situation where we talk about acid-base reactions, but then there are 2 chapters on acids and bases later on. Same with oxidation and reduction reactions. With redox reactions, there's another chapter later on that covers it in way more detail that again, this is just an introduction. It's a good preview of what you're going to be asked to do later on. So redox reactions, what are they? They're reactions in which one or more electron are going to be transferred between different species in your chemical reaction. So a good example of that is sodium and chlorine. So if we have sodium metal, which looks like this, we have chlorine gas. It looks like this yellow stuff here. It looks like it technically is mustard gas. And you mix them together. You get this violent reaction, but you make table salt, something totally safe and totally edible. Your body needs it. So what exactly is happening when you mix sodium and chlorine together to make your salt? So this is what the final kind of equation looks like, right? We've got Cl2, one of our diatomic gases, plus sodium, and we're making NaCl. So to balance that, I need a 2 here and I need a 2 here. But let's look at the actual sodium and let's look at the chlorine gas. So if I look at the sodium, here's what's actually happening. I have sodium metal, and sodium is turning into an ion. And when it does that, it loses an electron. Now, chlorine, on the other hand, is going to be turning into Cl minus. And so chlorine is going to gain 2 electrons here in order to make 2 chloride ions. And you might think, these don't add up, and they don't add up. So when we're doing redox reactions, what we normally end up doing is we have to have the same amount of electrons being gained and lost. So I would need to multiply all of those by 2. And when I do that, notice that the electrons on my product side and the electrons on my reactant side would disappear, and I'd be left with just this, Cl2, 2Na, and I would be left with 2Na plus and 2Cl minus to make my sodium chloride salt. So that's what a redox reaction is really all about. It's just losing electrons, gaining electrons, and you end up making new substances from that. Okay, so just keep that in mind. Now, there are rules for assigning oxidation states. And so it's kind of, if you're wondering, like, what's the point of this? The point of assigning oxidation states for different elements in a compound or elements just on their own, it's a way of keeping track of the electrons. And so there are rules that we like to use. So the first thing is that the oxidation state of an atom in an element is always going to be equal to 0. The second is that if we have a monoatomic ion, meaning like Cl minus or Na plus, your oxidation state is going to be equal to the charge of that ion. So Na plus has +1 oxidation state. Cl minus has a -1 oxidation state. Oxygen is always going to be an oxidation state of -2 in a covalent compound. There are exceptions where we have peroxides and then they're -1s, but we don't really deal with peroxides in here. Hydrogen, on the other hand, is going to be a +1 in covalent compounds. There are very few exceptions of that, by the way. Hydrides are 1, but again, not something you'll really be seeing very often. Fluorine is always a -1 when it's in compounds. The sum of all oxidation states have to be 0 in a compound. And we talked about that when we were naming compounds. So hopefully that rings a bell, that if you have an ionic compound, the overall charge on it has to be 0 if we're looking at a balanced ionic compound. The sum of the oxidation states is always going to equal the charge of the ion in a polyatomic ion. So for example, sulfate, SO4, 2-, the overall charge of all of the elements in it has to be equal to -2. So let's use those rules in order to figure out what the oxidation states are of each element in here. And I'm going to go through the logic of it, okay? So the first thing, if we're looking at our list, the first thing I would point out is that oxygen is mentioned. So oxygen is always a -2. I have 7 of them though, right? So let's think about this. If one oxygen is -2, how many would 7 be? Obviously, 7 times -2 is going to be -14. So even though one oxygen is -2, if I'm adding them all together right now, the overall charge, let's say, on all of these oxygens would be -14. All right, so picture that, -14. Great. Now, K. What's the charge on a potassium ion? So the charge on a potassium ion is a +1, and I have 2 of them. So even though this is a +1, I have now +2. So I have -14 and +2. That's overall a difference of, again, now I have -12 overall. So I have -12 overall. Okay, great. Now what about the Cr? So this is chromium here. Okay, it's in an ion. But now I have to, in some way, shape, or form, have the chromium add up to 12. So think about that. I have 2 of them, so that would be 6 overall. So overall, my chromium would have to be a +6. And so that would be correct. K would be 1, because I have 2 of them for a +2 overall. Chromium would be a +6, so that I can have +12. And then oxygen would be -2, and now I have, again, -14. So if I add those all together, 2 + 12 -14, the overall charge of this entire thing is 0. And notice there's no charge here. Potassium dichromate is just, a neutral ionic compound. All right, now let's try one that's an ion. Let's try this carbonate ion. So I have CO3 2-. So again, oxygen is always going to be -2. So if it's -2 times 3, that's -6. And I need to get this carbon. Now, what's the overall charge of this? -2. So what would the charge have to be on this carbon in order to get the overall charge of this entire thing to be a 2-? I think you probably figured it out. It would be a +4. So if this is a +4 and this is a -2, so +4 -6, the overall charge is now 2-, which matches this carbonate. Let's try another one here, right? So we have MnO2, we have manganese dioxide, which, by the way, if you're wondering why is it called that, even though it's not a covalent thing, it's a historical name, don't worry about it. So manganese dioxide here, we've got O2, so again, -2, that means that this would be a -4 overall. So what would manganese need to be if there's no charge here? It would have to be a, you guessed it again, +4. Now here's something that doesn't have oxygen in it anymore. Oxygen's one of those go-tos where everybody knows, okay, oxygen's always a -2. So let's try one where that isn't the case. Chlorine and fluorine are great ones. So chlorine, what's the charge on a chlorine normally? So the charge on a chlorine is normally a -1, and so we have 5 of them. So that means that would be -5. What would the charge need to be on this phosphorus then in order to balance that out? You guessed it, +5. And so +5 -5, you get 0. Perfect. Sulfur tetrafluoride. All right, so fluoride we already know is a -1, and again, that's 4 of them, so -4. What would the sulfur need to be then? You guessed it, +4. That's how you assign oxidation states for elements. So it's using all the rules that were on the previous slide. It's using the fact that you need to have all of the charges add up to 0 in neutral compounds like this, or to the charge on the ion if it's an ion. You need to look through your rules and figure out, like, okay, great, what can I fill in that I know already? And so normally you go for oxygens, or you go for hydrogens, or you go for halides. So you go for chlorine, fluorine, bromine, stuff like that, stuff that's really easy. Normally, there's always one thing in the compound, like chromium or carbon or manganese or phosphorus or sulfur, that you have to, like, use the clues of the other things that you already figured out the oxidation states in order to find that oxidation state. All right, redox characteristics. So in redox reactions, there's always a transfer of electrons. The transfer may occur to form ions, so you might make ions, you might make neutral compounds, it really just depends. And so what is oxidation? So oxidation is a process in which an element attains a more positive charge. So in other words, it's becoming more positive, or you can think of it as becoming less negative then, if we're looking at things that are already charged. And a good way to think of that is oxidation is losing, so that's oil. Now, reduction. What is reduction? Now, reduction is a little bit more confusing. So, reduction is a process in which an element attains a more negative charge. So, you're actually gaining in that situation. You become less positive when you are reducing something. And so, a good way of thinking of that is rig. So, reduction is gaining. So, oil is oxidation is losing. Rig is reduction is gaining. And what are we gaining? We're gaining, in this case, electrons. Or you can think about it from the case of charge instead. Redox characteristics. Last couple of definitions. Oxidizing agents are substances that accept electrons, and that means that they oxidize other substances. A reducing agent is a substance that loses electrons, so that means it reduces other substances. More on that in a bit. So here is a common biological example. We've got glucose and oxygen, and we're making CO2, and we're making water, right? So right here, we've got basically cellular respiration. Let's use those oxidation rules to find what the oxidation numbers would be of each one of these. And normally the way I start is, if it's just a pure element like O2, we automatically know that has to have an oxidation number of 0. And just in case you're wondering, do the coefficients mean anything? The coefficients do not make any difference here. You can just ignore them when you're assigning oxidation numbers. So let's go back to glucose. All right, what do we know about oxygen? What's oxygen always? You guessed it, it's always a -2. So I have -12 if I'm looking at all the oxygens. Hydrogen, what's hydrogen? +1. So that's +12. So that means that these are already balanced. What must the charge be on carbon? This is kind of weird. It's 0. And that is totally okay. It's okay to have something that's 0 in a compound. So that's that one. Let's go to this one. All right, so we've got CO2. We know that's a -2 times 2. That's overall -4. I've got +4 then. Here, got -2. Here, we know that hydrogen, again, is always going to be a +1 here. So that's all balanced. Now, looking at these oxidation numbers, what is going on, in other words? Okay, what is being reduced and what is being oxidized? So let's look at the ones, we can ignore the ones that are the same. Hydrogen's a +1 here, hydrogen's a +1 here. That's nothing. Oxygen, oxygen on this side is -2 and on this side's -2. But over here, it's a 0. That's kind of strange. Even here, look, carbon is 0 here, but then it becomes +4 here. So let's think about whether we have oxidizing agents or reducing agents. So glucose. So glucose, the carbon specifically, but glucose is losing electrons in this situation. Look, I go from 0 to +4. The only way to go from 0 to +4 is to lose electrons. If I'm losing electrons, now this becomes more positive. So that means that glucose, the carbon specifically, but glucose, because the entire thing gets wrapped in, is my reducing agent. Now let's look at the oxygen. So here the oxygen's -2, here it's -2, it matches. Here it doesn't though. So here it's 0, here it's -2. The only way to go from a 0 charge to a -2 is to gain negative things, to gain electrons. And so that means that my oxygen is gaining electrons, so that's my oxidizing agent. And in case you're wondering, that's why it's called oxidizing agent, because oxygen is a great oxidizing agent. And that's kind of why oxidizing or oxidation gets its name from oxygen. So that's just oxidizing versus reducing agents. Now let's actually do some concept checks here. Which of the following are oxidation reduction reactions? So I've got A, B, or C. Identify the oxidizing agent and the reducing agent. All right, let's take this one step at a time. Let's start with just A. So I know that any pure element is 0. Okay, and so that means that zinc is 0, and then guess what? Hydrogen's a diatomic gas, it's also 0. That's its, in its elemental form. But what about the rest? So let's start here. All right, I've got +1 for hydrogen, -1 for chlorine. Here, -1, that means -2 overall. That means that that's a +2. So look, my zinc is changing from 0 to +2, and my hydrogen is changing from +1 to 0. So thinking about what I know again, what does that mean? Zinc is my reducing agent. It's going from 0 to +2, and it's losing electrons to do that. And then HCl is my oxidizing agent. It's gaining. I'm going from, again, a +1 to a 0. The only way to do that is to, gain an electron. And if I gain an electron, now I have an oxidation number of 0. So zinc and HCl, that is a redox reaction. All right, let's try B. So again, here there are no pure elements in their common forms here. So -2, okay, 7. 7 times -2, that means that that's, -14. And I need to get my chromium. So that would have to be a +6. All right, so now, and then those add up. So I have +12, -14, that gives me my -2 charge. All right, over here, I've got a -2 for my oxygen. I've got a +1 for my hydrogen. -2 and +1, that gives me a minus charge. That's fine. All right, let's go to over here. So I got my -2 times 4, that's -8. Chromium needs to be a +6. All right, over here, -2. Over here, +1. +2 -2, that gives me my neutral charge here. Notice, hey, look, all of these are the same. +6, +6. -2, -2, and -2. +1, +1. That means that nothing is going on here. This is not a redox reaction. So B is definitely wrong. All right, let's try C. I've got copper 1 chloride, and I'm making copper 2 chloride and copper metal. So again, this is in pure form. This is all by itself, so it's always going to be a 0. Here, I've got a -1. I've got a +1. Here, I've got a -1. I have -2 then overall, so that means this has to be a +2. So look, the Cl is the same, but the copper is changing. It goes from +1 to +2, +1 to 0. And so the reason why I chose this one is because technically, if you have two of the same thing, one of them can be acting as an oxidizing agent and the other can be acting as a reducing agent. So in reality, each one of these is going to be a reducing agent and an oxidizing agent. One of these CuCls is going to be the reducing agent. It's losing electrons. And then the other one is going to be the oxidizing agent, and it's going to be gaining electrons, because one of them is going from +1 to 0. The other is going from +1 to +2. And so, again, that's just kind of a good concept check for oxidation and reduction reactions. All right, so now that we've done all of the work for A, B, and C, we're finally able to answer the question. So A and B are oxidation reduction reactions. And then to identify the oxidizing and reducing agents, we already did that on the previous slide. So only B was not an example of an oxidation reduction reaction. All right, last slides here are about section 4.10, balancing oxidation reduction equations. So keep in mind that, like I said, there is an entire other chapter in the book all about redox reactions. So for now, we're going to teach you one method for balancing oxidation reduction reactions, and then later on in the book, they will teach you a couple of other ways of doing this process. But for now, these are really the only steps you need to identify and be able to use when you're balancing something like a redox reaction. So the first part, write the unbalanced equation. So that's nice and easy. Next, determine the oxidation states of all the atoms. 3, show the electrons gained and lost using tie lines, and I'll show you what tie lines look like. 4, use coefficients to equalize the electrons gained and lost. And then 5, balance the rest of the equation by inspection. And that basically is a fancy way of saying check your work and make sure everything looks good. So let's do that for a real example. So balance the reaction between solid zinc and aqueous hydrochloric acid to produce aqueous zinc 2 chloride. And so zinc is always a +2 in an ionic compound, so you actually don't need to put the Roman numeral 2 there. I don't like that the book did, but it's just zinc chloride. and then hydrogen gas. All right, let's do that. So let's write the unbalanced equation. So just off the top of your head, zinc metal, hydrochloric acid, we're making zinc chloride, and we're making hydrogen gas. So you should be able to identify zinc, hydrogen gas, it's a diatomic gas. Hydrochloric acid is HCl, and then zinc chloride is ZnCl2. All right, next, what are the oxidation states? So now it becomes a little bit more interesting. I always like to go for the ones that are in their pure form first. So zinc is a 0, and hydrogen gas is going to be a 0. The other part, though, here, that's a lot more interesting. So let's use our rules. Hydrogen's a +1. Chlorine has to be a -1 then. Zinc +2. Why? Because Cl is a -1, and there are 2 of them. So that adds up to a -2, and we have to balance that out with a +2. All right, now that we've done that, let's take a look. How many electrons are gained and lost? Now, this is where we use tie lines. So what's changing here? Chlorine is staying exactly the same, but zinc is going from 0 to +2. Hydrogen is going from +1 to 0. So a tie line is basically a bracket. It looks like this. So notice that to go from 0 to +2, I had to have lost 2 electrons. So zinc lost 2 electrons. And remember, that means that that would be oxidation. Oxidation is losing electrons. So zinc is actually undergoing oxidation. Hydrogen, on the other hand, is gaining an electron. It's going from a +1 to a 0. So it is going through reduction in that situation. Remember, reduction is gaining. And like I said, keep in mind, chlorine remains unchanged in the reaction. It's just kind of like hanging out. Now, what coefficients are needed to equalize the electrons gained and the electrons lost? All right, so if I had 2 electrons lost but only 1 electron gained, I need to double the amount of electrons that I'm gaining in order to have these be the same. Otherwise, it won't balance. So I'm going to need to put a 2 where the HCl is in order to keep that balanced. And notice that now, if I put a 2 here, that means that I have 2 H2s, and I have 2 Cls. That means I have 2 Cls, so everything is balanced in that situation. Now, something else, though, here's a little bonus. What is the net ionic equation? So the net ionic equation, if I were writing it out, I would have to take my HCl, because it's aqueous, and break it apart. And so since there are 2 of them, that 2 applies to both things. And then same thing with zinc chloride. Zinc chloride, we've got a 2+, we've got a -1. And so that means that we've got, again, our nice little breakdown here, let's say. And so how would I write the net ionic equation? Well, what's my spectator? The only spectator ends up being the thing that didn't actually undergo anything in the reaction. The Cl was my spectator, and so I would get rid of those. And so I'd be left with zinc plus 2 H pluses, gives you Zn2+, and gives you H2 gas. And so that's it. So if you have any questions, please let me know. But generally speaking, that's kind of it for chapter 4.